Okay, thank you very much. Sorry for not being there, but I actually I woke up at 3 a.m. this morning to listen to the talks this morning, and they were all quite good. So thank you very much. So I'll talk to you about lattice simulations of nuclear structure. This is work done with the Nuclear Lattice Effective Field Theory collaboration, and you will see many of my collaborators on the papers that I will show you here. Okay, so here's the outline. I'll first talk about lattice effective field theory, the main tool that we use for the calculations. Then I'll talk to you about nuclear physics near a quantum phase transition. I talked about this last time in the online version, but I'll repeat some of the main points here. Then I will talk about spin isospin exchange symmetry and how that comes from the large NC limit of quantum chromodynamics, where NC is the number of colors. And then I'll talk about the essential elements of nuclear binding before focusing on the structure of carbon-12 states and the Hoyle state. Then I will talk about some work in progress on wave function matching, how we are able now to do calculations of many body systems at N3LO in chiral effective field theory. And then I'll summarize. So we do simulations of protons and neutrons on a lattice with a lattice spacing between, let's say, half a Fermi to up to 2 Fermi if we're doing dilute neutron matter. If you want to learn more of the technical details of what we do, I have a now relatively old review article, but there's a nice textbook by my collaborators, Timo Lede and Wolf Meissner on the subject. So if I compare lattice effective field theory and lattice QCD, you can see here the strongly interacting phase diagram. Here on the horizontal axis is the density of nucleons per cubic Fermi. And on the vertical axis is the temperature in megaelectron volts. And lattice QCD can carve out this part of the phase diagram, but it can't go beyond a certain angle here, if you like. Yeah, sort of like a wedge shape because of the sign problem, because of Monte Carlo simulations getting positive and negative weight contributions. But it can go to essentially arbitrarily high temperatures. With lattice effective field theory, by changing the degrees of freedom, we can actually go to higher densities at lower temperatures. But there is a maximum density we should not go beyond some factor times the saturation density. And there's some maximum temperature we should not go beyond, because then we start seeing hadronic degrees of freedom beyond the nucleons. But there's a quite interesting region here where there's an overlap between the two methods, and there's lots of nice physics here. And I won't talk about it, but you can do things like nuclear liquid gas transitions, and we can look at neutron superfluids, but I won't cover that in this talk here. So what we do is we put chiral effective field theory on the lattice, and the chiral effective field theory is described in the way that Weinberg first showed us how to do it, but there are other ways of doing it now. It's essentially an effective interaction between the nucleons coming from the mediation of pions and shorter range exchange forces, or in the language of chiral effective field theory, they're just treated as contact interactions at some short distance resolution scale. So at leading order, what we're doing is just counting powers of momentum in this effective field theory, but at leading order, or 0 powers of momenta and also 0 powers of the pion mass, we have the exchange of 1 pion, or the 1 pion exchange potential, and we have then the S-wave contact interactions. And then beyond leading order, we have things like the 2 pion exchange potential and higher contact interactions that have more powers of the derivative. So what we do now is we tune up the unknown short range coefficients to reproduce what's seen with scattering of nucleons. So here you can see with the lattice spacing of 1.3 Fermi, the spin singlet S wave phase shifts, the spin triplet, and the mixing angles for j equals 1, j equals to 2, the spin singlet, spin triplet P waves, spin singlet and spin triplet D waves. What we do is we take the empirical data, which are the solid lines, and try to reproduce by tuning the unknown short range coefficients try to reproduce empirical scattering data. So you can see here at next leading order, next to next leading order, and N3LO. As you can see, as we go to higher orders, we get a reduction in uncertainties and a better agreement with data. And if we also decrease the lattice spacing a little bit, we get also a slightly better agreement with empirical data. So now, why do we put all this stuff on the lattice? Well, it's not to do scattering, because scattering is much easier to do in the continuum. It's to do the many-body system, to go beyond 2 or 3 particles or 4 particles. So the way we do this is by using Euclidean time projection, which is sort of the standard technique used for quantum Monte Carlo simulations. What we do is the exponential minus h tau. So h is the Hamiltonian, and tau is the imaginary time or Euclidean time. So there's no I here. What this does is it gives us a low energy filter. The high energy states of the Hamiltonian get exponentially damped, and the low energy states survive the longest. Now, the Hamiltonian contains a term that's like the kinetic energy term of the nucleons. And so if I exponentiate this with the kinetic energy term, or an exponential of, let's say, positive del squared over 2m times tau, then this is a diffusion operator. So a diffusion operator can be modeled exactly by a random walk of particles. So we can think about these nucleons as executing a random walk in space as a function of the Euclidean time parameter. And so that's what is drawn here. We have tau equals to 0 as the initial time, tau equals tau final as the final time. We have these nucleons doing a random walk in space as a function of Euclidean time. Now, we also have interactions, and so we have the exchange of a pion, and we have short-range interactions that are taking part as well. So the way we actually do the calculation, though, is with an auxiliary field. And so what we do is we rewrite the interaction. So let's say we have this short-range 2-body interaction, n dagger n squared, and we want to take the exponential of minus h tau with this interaction. So we have something like this exponential of minus c over 2 n dagger n squared. So now we can think of n dagger n as some real variable. And I can rewrite this top line as the integral from minus affinity to plus affinity of an auxiliary variable, ds. And with a weighting, that's a Gaussian function with a linear shift. Okay, this linear shift is, we can see we have a quadratic form here. And you know how to do this integration. What you need to do is you need to complete the quadratic form. And the term that's missing is exactly the term that's up here on the first line. So if I do this integration, I cancel the 1 over square root of 2 pi, and I get exactly this term exponential minus c over 2 n dagger n squared. Now, the reason this auxiliary field is helpful is because now the nucleons don't interact with each other. They interact with this auxiliary variable. And so they essentially have now decoupled from each other, but we get the interaction back when we integrate over the auxiliary variable. So we have this auxiliary variable, this auxiliary field, at every point in space and time. And by integrating over that auxiliary field, we recover the interactions that way. But what we've succeeded in doing, though, with this auxiliary field is decoupling the nucleons at the level of this background field. So the single nucleons then just interact with the background field, as well as interacting with the pion field. And so what we do now is we consider the single nucleon amplitude coming, originating from a nucleon initial state J to a nucleon with the final state I. So we then have a matrix of amplitudes, G sub ij. So if I have a nucleus with A particles, this is an A by A matrix, then it's a function of the auxiliary fields as well as the pion fields. And then to calculate the many-body amplitude, we calculate the determinant of this matrix that multiplies the single nucleon amplitudes together and anti-symmetrizes. That gives us the determinant. So what we then do is we put this on a supercomputer, we update then all these auxiliary fields and calculate then the many-body amplitude. So then what can we calculate? So let me tell you about this nuclear physics near quantum phase transition. So one study we did back in 2016 was we considered two different interactions, A and B, at leading order in chiropractic field theory. And they both had essentially the same phase shifts. Back then, they were only approximately the same phase shifts, but we can now do this analysis these days with exactly the same phase shifts and come up with exact same conclusions that I will present to you in just a moment. But basically, A and B have the same phase shifts at the two-body level. Okay, the only difference between A and B is that they're short-range interactions, meaning not their pion exchange, not the Coulomb potential, but their short-range interactions are slightly different. For interaction A, the interactions are very much non-local. And for interaction B, there's a mixture of non-local and local. Now, I should explain what I mean by local. What I mean by local is something like the Coulomb potential, in that it's diagonal in position space. So if I write down the interaction in position space, it's diagonal. It's just a function of the positions of the particles. The incoming particles have the same positions as the outgoing particles. A non-local interaction is one in which the incoming and outgoing positions of the particles could be different while preserving the center of mass position. Okay, so that's the difference between A and B. A has purely non-local, whereas B has some mixture of local as well. And what we found is that by doing these calculations of alpha scattering, so this by itself is a whole long story how to do this calculation, but let me just assure you that we know how to do these calculations ab initio, these 8-body system calculations of alpha scattering for the S wave. And so the phase shifts look something like this. For interaction A, we get, so let's just look at the data with the Coulomb included. So for A, we get these diamonds here, and they're quite a bit different from what we get with the empirical data, which are the asterisks. So the horizontal is the lab energy, and this is the S wave phase shift, whereas interaction B is pretty much on top of the empirical phase shifts. So what you see is that the interaction B is able to get quite a bit of attraction between the alpha and the alpha, which give you an almost bound Brillouin mate. Whereas interaction A, which had essentially the same phase shifts, and nowadays we can actually make them have exactly the same phase shifts, we can essentially make the alpha-alpha interaction negligible. In fact, it becomes repulsive at higher energies. Okay, so that tells you that the alpha-alpha interaction is not purely determined by the nucleon-nucleon phase shifts, but are determined by other features. And so what we're saying is that the local part of the interaction actually plays some role. And the underlying physics of this is the fact that the nucleons are somewhat, the alpha particles are somewhat compact objects, and the local interaction is more coherent in producing an attractive interaction between the alpha particles, whereas non-local interactions are less coherent in producing an effective alpha-alpha attraction. Okay, so you can then essentially, with the same phase shifts, you can interpolate between different two nucleon interactions and produce a quantum phase transition, where on this side we have a system with interaction A, where we have actually the alpha-alpha interaction is so weak, we don't bind any nuclei, N equals Z nuclei beyond the alpha particle. They just fall apart into an alpha gas, Bose condensate. But there's some point at which the alpha-alpha interaction becomes attractive. And at that point, if we have enough particles, we form a large droplet. And if we increase again the local attraction, we get to the point where, let's say, neon 20 is bound, oxygen 16, carbon 12, and then at some point, the beryllium 8 also becomes bound. So this is our picture of what's going on here. You can read more about it in this paper here, that there's a quantum phase transition that actually nuclear physics is not so far away from if the interactions did not have sufficient amount of local attraction. Now, you might ask the question in nature, what provides this attraction so that we're not over here, that we're more over here, essentially somewhere over here? And this seems to be produced by the 2-pi exchange potential, which has a spin-independent, isospin-independent attractive local force that comes from 2-pi exchange. Okay, so let me now make this, this is a nice segue then to understanding the properties of the nucleon-nucleon interaction and how that affects the nuclear structure that we see. So I'm going to make a connection to fundamental physics here and make a connection to quantum chromodynamics. So let's consider quantum chromodynamics, where NC is a number of colors, so that the gauge group is SUNC. And let NC not be 3, which it is physically, but be a large odd number. Odd is important so that then the nucleons are fermions. Okay, as we take NC to be odd and large, it turns out that the ground state of these baryons, now they become heavy because what we now have are these quarks. You have NC of these quarks, okay? And so we'll have quite a large number of quarks. And so the wave function of these heavy baryons with large numbers of quarks will actually be a Hartree-like state, some sort of very simple tensor product where the quarks have the same spatial wave function, but they have some interesting group theoretic structure for the spin and isospin. And it turns out, if you look at the pairing channels that you can get for the quark interaction, is you find that the lowest energy state, the ground state for the nucleon, will be spin 1/2, and the ground state will also have isospin 1/2. So this is actually quite interesting that the nucleons, the ground states will have spin 1/2 and isospin 1/2, even though NC is very large. This is to some extent a fine tuning that the arrangement of the spins, which could be as large as NC, is actually only 1/2. It's the same thing for the isospins. So what this means is if you measure the expectation value of an operator like Q bar Q, which counts the number of quarks, this will be as large as NC. It scales with NC. Whereas if you measure an operator like Q bar sigma, where sigma is the Pauli spin, Q bar sigma Q, you get something that's 1/2, which is very small, or suppressed by a factor of 1/NC. The same thing for tau, where tau is the isospin operator, the isospin matrix, if you want. If you have Q bar tau Q, this is also anomalously small. It's going to be equal to 1/2 when acting on the nucleon. And so that's also fine-tuned. But if you measure something like Q bar sigma tau Q, where you have spin and isospin, there's no reason why that needs to be a 1/2, and this will actually be of order NC. So now you can analyze what is the effective interaction between these now relatively heavy nucleons. They're heavy because there's lots of quarks in them. So the fact that they're heavy tells you that the interaction will be a local interaction. It won't be able to move the nucleons because they're heavy. So you get an effective local interaction. And furthermore, you will not have an interaction that involves just sigma or just tau. You will either have no sigmas, remember sigmas for spin, taus for isospin, or you have both spin and isospin at the same time. So you have this underlying sort of spin-isospin exchange symmetry in the sense that wherever you have a sigma, you must also have a tau, or you have neither one. So you have this interesting structure that this was first derived by Kaplan-Savage, Kaplan-Manihar, trying to understand the large NC limit of the nucleon-nucleon interaction. So you have this local potential, which is independent of spin and isospin, a central interaction, if you like. And then you have another local interaction that has this spin-dot-spin, isospin-dot-spin coefficient to it. But then you can also have this interaction, which breaks the spin-isospin exchange symmetry, which is the tensor force that's coupled to tau-dot-tau. So it has to have this structure tau-dot-tau. But what's interesting is that if you are going to consider an object where you average over the intrinsic spins of the system, then the tensor force will average to 0. That's just the nature of the tensor force. It's traceless in intrinsic spin. Then you actually eliminate the expectation value of this term, and you recover a very nice spin-isospin exchange symmetry. So this is explained in this paper. This was actually, by the way, also pointed out by Kelly, Gordon, and Ariola back in 2009. We examined this a bit further and trying to understand more deeply the derivation of how this all works. But here's something really interesting that you can find is that if there is a optimal cutoff momentum in which this derivation holds, in our paper here, we actually showed that if the cutoff is too high, then this derivation does not work, because what happens is the nucleons are no longer in their rest frame, and you have to consider then the boost, what happens to the boosting of the wave function of the nucleon. Similarly, if the cutoff is too low, then you cannot resolve the difference between the intrinsic spin of the nucleon and the orbital angular momentum of the nucleons. So if the cutoff momentum is on the order of about 500 MeV, everything works, and you get this spin isospin exchange symmetry, sort of a hidden spin isospin exchange symmetry appearing. And you can see it like this. Take the spin singlet phase shifts. Here's the spin singlet phase shifts as a function of relative momenta. And then consider the spin triplet phase shifts, which look very much different. Okay, but now what you do is project onto L equals 0. So you're essentially removing the coupling to the D wave, which comes from the tensor force. If you do that, what you find at this cutoff momentum, that you get phase shifts that are very similar to the spin singlet phase shifts. So you get this restoration of the spin isospin exchange symmetry. You can do the same thing for the spin singlet and the spin triplet D waves. You have the spin singlet D wave here. You have all these different spin triplet D waves. But if I now do again a spin intrinsic spin average, what you'll find then is for these the D wave averaged over intrinsic spins, you get something very similar to what you get for the spin singlet. So you see that there's this spin isospin exchange symmetry underlying the nuclear interactions if you have a cutoff scale that's comparable to what is often done in chiral effective field theory. And it also gives some motivation to why Weinberg's original idea and why Weinberg's power counting actually seems to work. Okay, but it also shows you that there seems to be some underlying Wigner SU4 symmetry. If I restrict myself to the S waves, right? If I just restrict myself to the S waves, then this sigma dot sigma tau dot tau is just a number. And so this is an SU4 invariant interaction. I'm now neglecting the effect of the tensor force here. Okay, so if I'm looking then at some sort of spin average or intrinsic spin average quantity, some sort of bulk properties where we're not specifically looking at spin orbit interactions, then we will see then the emergence of this SU4 Wigner symmetry where the proton spin up, proton spin down, neutron spin up, neutron spin down, or four components of an SU4 symmetry. Okay, so this is then what we found with this. This is what we studied then in this paper, where we look at the essential elements of nuclear binding. So we wanted to know what are the minimal interactions that can reproduce the ground state properties of light nuclei, medium mass nuclei, and neutron matter simultaneously with no more than a few % error in the energies and charge radii. And so what we found was that we can take 3 parameters that are just tuned to the 2-body and 3-body system. And then with 1 parameter, we can do a pretty good job of reproducing 80 or so even nuclei. So that's what you see here. The experimental results, the empirical results are in the open symbols, and the lattice results with this very simple 4-parameter interaction are with the field symbols. And so the 3 of the parameters are just tuned to these guys here, and 1 parameter is tuned to the rest of them. And by the way, this is, controlling this extra parameter is controlling the alpha-alpha interaction. And so you can see it does a reasonable job of reproducing the data for various nuclei, the binding energies and the charge radii, even though it's a very simple interaction, and it can reproduce in the charge density distribution for oxygen 16 with the Coulomb interaction included. Same thing for calcium 40, although there's a little bit of an overshoot in the central density, but it's a pretty good description for a very simple 4-parameter interaction at the microscopic level. Okay, so at this point, I'm going to now transition to talking about carbon-12. So you can take this very simple interaction and look at what happens in carbon-12. And so this is a paper by Shihang Shen, who's a postdoc with my collaborator Ulf Meister in Jülich, as well as Timo Lede. And so last year, we took a look at what we would get with different lattice spacings, 1.97, 1.64 Fermi. I should mention that these lattice spacings look large, but we actually, this data is with 1.3 Fermi, but the point I want to make is that we actually get sub-lattice spacing resolution in the one-body densities because the center of mass of a nucleus is not on a given lattice site, but it's actually a fraction of a lattice site. So if I have capital A being the number of nucleons, then the center of mass of the nucleus is actually on a lattice site divided by capital A, and that's why we actually can get sub-lattice spacing resolution. And it does a pretty good job of reproducing the low-lying states of carbon-12, as you can see here. But we were interested in trying to see what structures we could actually find. And so after we did that calculation, we then took a look, this was again Shen, in this preprint here, took a look at the actual structures of all these low-lying carbon states. So what we found is that there was a nice duality appearing, that there were a lot of states that we could reproduce by shell model initial states like the ground state of carbon-12, as well as the first 2+ state and the first 3- state. However, we also could see very clearly by looking at the intrinsic densities, there was clearly also an alpha cluster structure underlying these guys. So even though we can reproduce these structures quite nicely with shell models, we see there are correlations within that shell model structure that we can see these intrinsic shapes. So here's a plot of the various angles. So if we have these clusters, 3 clusters here, we can measure the angles between the sides, the vertex angles, θ1, θ2. And what we see for the ground state is essentially an equilateral triangle, 60-60. Okay, same thing for the first 2+ state, and same thing for the first 3- state. But if you look now at the Hoyle state, what we find is that the angles are much wider. And so we see it's it's more than 120 degrees, in fact, the angle. And we see this kind of bent arm obtuse triangle shape. Same thing for the second 2+ state, suggesting that these are related they are connected by a rotational band. There is actually a third 0+ state that has a similar structure, but if you look very carefully, it seems to have a slightly different structure here, suggesting there might be some sort of a vibrational excitation or something else going on. This requires further exploration. But we can then look at other structures like the first one, the 1- state, the second 4+ state, and so on. And so all of these seem to have this equilateral triangle structure to it. These all, by the way, have a very simple shell model structure, so we can actually produce these with nice overlaps with shell model states, but at the same time, they have these equilateral triangle shapes to them. Now, then there are more exotic structures which don't have such easy shell model overlaps, but we were able to see that they also have either equilateral triangles or these bent arm configurations. So what we seem to be finding is that all of the low-lying states of carbon-12, including the ground state and the Hoyle state and everything else, seem either to have this equilateral triangle shape to them or have this obtuse triangle shape to them for all these states. So the empirical results are in the stars, the results I showed you are in the squares, and the old result from 2021 with 2 different lattice spacings are in the circles and the pentagons. Okay. Now, at this point, I'm going to spend the rest of my time talking about something new that we're doing called wave function matching. So here you see this is supposed to be just a little cartoon explanation. So we have something that we want to simulate that's complicated with lots of fine details, something high fidelity. But then there's something familiar, and this is a picture of my cat, Sophie, something we like, we know how to do, something we can deal with. But we want to be able to use this to help us do something that's high fidelity that we can't do directly. So the idea of wave function matching is to take some short range part of the thing that we are able to deal with and replace the short range physics, the short range correlations of the thing we are trying to do with the thing that we are familiar with. Now, this might sound a lot like the renormalization group methods like the SRG, similarity renormalization group methods that you've probably heard plenty of talks about by my colleagues Scott Bogner, Achim Schwenk, Dick Fernstall, and others who have pioneered this, and Heiko Hergert for the medium SRG. But this is actually something completely different that I will tell you about today. And this is work in progress led by Sardar El-Hattasari and Lucas Boverman. Okay, so what is the problem we're trying to solve? So lattice Monte Carlo simulations can compute highly non-trivial correlations in Euclidean many-body systems. Unfortunately, sine oscillations prevent direct simulations using a high-fidelity Hamiltonian. For example, let's say an N3LO chiral effective field theory Hamiltonian with strong tensor forces that have short-range repulsion, and these short-range repulsions produce a sine oscillation in our Monte Carlo simulations. So this is a problem. Now, wave function matching solves this problem by means of a unitary transformation and perturbation theory. Okay, this additional piece of perturbation theory is what makes it quite a bit different from SRG, similarity renormalization group. Okay, so by using unitary transformations, what we are doing is we construct a high fidelity Hamiltonian that can be reached by perturbation theory starting from a Hamiltonian without a sign problem. This is specifically for Monte Carlo simulations. You might be using some other many-body technique, but you could use it to start from some Hamiltonian that you can calculate with. So here's what's going on. Here's a set of non-perturbatively computable Hamiltonians, or directly calculable Hamiltonians. And here's a Hamiltonian, high fidelity Hamiltonian you really want to calculate. Let's say it's an M3LO chiral interaction. So the idea is we take a unitary transformation that produces the same high quality phase shifts as this interaction and do a unitary orbit and find a point that's close to this set over here. Now, if you can actually pass through it, then you're all set. But let's say you can't actually pass through it, but you can come very close. If you can do that, then you use this new Hamiltonian H prime A, and we can use perturbation theory then to do these non-perturbative Monte Carlo simulations, and by simple first order perturbation theory, get very accurate results already at first order perturbation theory. And this is the idea of wave function matching. If you want even higher precision, you can obviously go to beyond first order, go to second order, or use some non-perturbative method like eigenvector continuation. But let me show you how this works. Okay, let's suppose we have a interaction VA that's difficult for Monte Carlo simulations because it has a hardcore repulsive term here. Okay, but let's say we have VB here that doesn't have this repulsive core. It's just attractive all the way through. Okay, so if I now compare the phase shifts for VA and VB, at low energies, they look kind of the same. You can't really resolve them, but you see at high momenta, VA is different because it crosses zero and it becomes repulsive, whereas VB never crosses zero. It's a soft interaction that is attractive all the way through. Okay, but now let's try to use perturbation theory anyways, even though these guys look quite a bit different from each other. So let's write the eigenenergies and eigenfunctions for the two interactions. So let's say HA has eigenstates psi A n and energies EAN. Let's write K for the kinetic energy. Let's just work in the two-body system here. VA is the interaction. And the same thing, K is the kinetic energy, VB is the interaction, and the eigenstates for HB are psi BN, and the energy is EBN. Now, we would like to compute the eigenenergies of HA. We would like to compute the energies of HA starting from the eigenstates of HB, because let's say we can calculate it with HB. That's easy for us, but we want to calculate the energies for HA. And we're going to use first order perturbation theory. Okay, so let's do that and see what happens. So here are the exact energies for EAN. So you can see here are the energies. And here is here are the wave functions for HB, and just taking first order perturbation theory is essentially just getting the expectation value of HA. All right, so you see this is pretty terrible. This does not really do a good job. All right, so this is not going to work very well at all. But what can we do? What we can do is we can now use wave function matching. So what we do with wave function matching is we essentially take the short range piece of the ground state of psi A. So to do this formally, I take P to be a projection operator that cuts out only the short range piece of the wave function. So P acting on psi 0A gives me the short range piece of that guy, but I'm going to normalize it. I'm going to divide by the norm of that short range piece, because that's what I need to define a unitary transformation, a normalized state. And I'm going to map that to the short-range piece of psi b ground state, also properly normalized. So my unitary transformation will map the short-range piece of psi 0, the ground state of A, to the ground state of B in the short-range piece. Now, the rest of the unitary transformation really doesn't matter that much, but what we do is we use Gram-Schmidt orthogonalization to fill the rest of the unitary transformation. The important thing is that now we can write down a new interaction H prime A, which is U dagger H A U. And that corresponds with some new interaction just by subtracting off the kinetic energy term. So that gives us a new interaction VA prime. So now I can compare then the phase shifts for VA and VA prime, and they're exactly the same because it's just a unitary transformation that connects the two. So VA prime has the same repulsive interaction at high momenta. Okay, but now what we can do is we can look at the ground state wave functions. What has happened to my ground state wave function? Here is a high fidelity Hamiltonian that was difficult for us. And here is the nice interaction that we could simulate. What we've essentially done is we've taken the short range piece of psi b, properly normalized, and done plastic surgery and removed this piece of psi a that we couldn't deal with, and just essentially stitch those two together to make sort of a Frankenstein wave function. That's the actual exact ground state wave function for HA prime. Okay, so how does this help us? Well, the point is that psi a prime looks a lot like psi b because the tails are approximately the same, because the tails, these tails were kind of the same. And the interior part of psi a prime is essentially modeled after psi b. So that suggests that perturbation theory might actually work starting from the Hamiltonian HB. In fact, you can see it does. So here is what we showed before, the exact energies EA. Here are the energies when we try to do naive first order perturbation theory. It doesn't work. But now if we use the new interaction HA prime, we actually do pretty well. When we recover at first order perturbation theory, the energies to within a few tens of keV. And if we went to second order, this would be extremely accurate, but first order seems to be quite sufficient. Okay, so this is how this works. And so we've now implemented this. Our paper will probably be on the archive in the next 2 weeks. So we've done now with wave function matching, chiropractic field theory calculations at M3 low using wave function matching, and gone up to A equals 40 nuclei. And we can reproduce then the binding energy per particle with an RMS error that's pretty good. At the level of binding energy per particle, it's something like 0.1 MeV binding energy per particle. And at the same time, once the binding energies are good, everything else actually are also good. The charge density profiles are also good. You may know that there's sort of this lingering problem that very often the binding energies or the saturation properties might be good, but the radii might be not so good with these ab initio calculations, but we seem to be getting everything to line up pretty well. So the way you should read this experimental, I don't know why we have two different sets of experimental data. One of them is clearly much better than the other. But yeah, just look at these experimental data here, empirical results, and then look at this. So this is Euclidean time. So essentially we're extrapolating to infinite Euclidean time. So just look at the last one at 0.3. So you can see it's in reasonable agreement with empirical data here for calcium 40. And we can then calculate with for pure neutron matter up to about 1.5 saturation density. This is our neutron matter results for the energy per particle. This goes up to 80 particles, okay? And it's in pretty good agreement with other ab initio calculations of neutron matter. And here's then also the symmetric nuclear matters. We go up to about 140 nucleons for these simulations. And what you see is that we do a decent job of the saturation point. It seems like we are at about 0.9 times the saturation density, and we go down to about maybe 17 MeV rather than 16 MeV, but we did not tune to this at all. This is a prediction. We did not use saturation at all to tune the three-body interaction. I should mention that our interaction is qualitatively different from other calculations. So for example, here's the delta full N2LO calculation by the Oak Ridge-Gothenburg group, which gives this curve here. I should mention that our results are qualitatively different because we do unconstrained lattice simulations. We actually get phase separation at low densities. So if we did a simulation at infinite volume, we would actually have a straight line here going all the way to zero density. But because we work at finite volume, finite number of particles, it starts to curve up because of surface to volume effects. But that's why we don't sort of tend towards zero as we go to, it looks a bit different because we get phase separation in the simulations themselves. Okay, so let me summarize now. So I started with the introduction to lattice effective field theory, then showed that symmetric nuclear matter is near a quantum phase transition, and talked about some larger NC arguments that nuclear physics is close to Wigner's SU4 symmetric limit. Then we studied nuclear states of carbon-12 and found that alpha cluster structures with two different geometries. And then we concluded with a discussion of wave function matching. So I'd like to thank you very much for your attention, and I'd be happy to answer questions.
Thank you, Dean. So excellent talks.